I promised you that I would give it today, I want to resume the discussion of yesterday concerning the Paizulenbeck oscillator. So as you remember, we were discussing the quantization of this guy using path integrals. So, quantization. So let's just remember the Lagrangian of these guys. So it was something like that. Omega 1 square, d squared, dt squared, plus omega 2 square, q minus v of q. And then you do a given coordinate transformation, then this just look like minus q2 dt square plus omega 2 square q2 plus q1 d2 dt square plus omega 1 square q1 plus given, I think it's q2 minus q1, given potential transforming these new coordinates. And then we saw that if we put the potential equal to 0, then the path integral completely factorizes into one contribution, which I'm going to write in this way, and another contribution that I'm going to write in this way. So it's S2, in which, you know, S1 is just this guy with a minus sign. S2 is just this guy here, right? And then those integrals are completely in a way that we can calculate, but always adding a term to make these integrals convergent. So make the integrals convergent. So in the end, we also add some external sources. And then in the end, we show that the path integral in terms of these sources can be written in this way. So J plus, J minus. I'm considering J plus is associated with the Q2 and J minus is associated with K1. So it's just something like that. So let me just write something like this. J plus, J minus, where Z of J plus minus is equal to an exponential just given by dt prime, J plus minus T, something that is associated with a propagator, G plus minus T prime. And this guy, the propagator, has this form. T plus T prime. And I here, so it's an integral over 2 pi minus I, and a minus I, T minus T prime. Let's just put it in this way. Minus T and a minus T, omega square minus omega 1, 2 square. So if it's 1, it's minus. If it's 2, it's plus I epsilon. Right? Because these path integrals have different signs in here, so the epsilon here enters in both integrals with different signs, right? So what we were discussing is that, okay, so now we have a closed result, and what does that mean? What does that mean? It means that we have now two oscillators, right? But with different notions of causality. That was the point that we stopped yesterday. And why is that? Because causality here is associated with the signs of I epsilon. So I epsilon dictates what we call the arrow of causality, which you can define as the time direction in which causal quantum process occur. So now we have to make a distinction between time directions and causal directions. These two things in here measure time different ways. So for instance, this guy here, which would be the normal oscillator, for him, the arrow of causality is aligned with increasing time. So the convention of measuring the time here is just as we would usually take, right? But this one here aligns its causal direction backwards in time. So for this guy here, the convention is backwards in comparison with this one. And both guys are living here. If we take both path integrals in separate, both path integrals describe quantum processes just as good as the other. The only difference is to make about the way that you're going to consider the measure of time. So this is a good path integral, and this is also a good path integral. The only difference is how you're going to measure time. Mm-hmm. By that you mean other situations where you have these higher derivative terms here? Yes, that's what we're going to see today. But then, taken in isolation, you have a very good notion of what is causality. But in our case, we are seeing that the both things are happening together. So we have two arrows of causality in our model. In our case, we have two arrows of causality. But that makes problems to us, because then we cannot define what causal is. We couldn't define what is, in which direction causal process should occur. And that, of course, violates everything that we see in nature, right? At least in a certain low energy context, right? So there must be something out of this controversy. There must be something that we could do to get us at least a notion of causality, at least in a certain context. But then for this, you have to define in a certain way what do you mean by the guy or the guys or the set of guys that are going to give you the dominant concept of causality. Yes. Yes, that is why the I epsilons are here. We we didn't drop the time order. No, we didn't. No, no. If we're not dropping the time order, actually. That is why the I epsilons are appearing. I epsilons mean that you are considering an expectation value or product of time ordered fields. That's why the I epsilons mean. But that's an output. I'm not imposing this. That is just an output. So causality is an output in this sense. But the problem is, there are two notions of causality here, two notions of causal process. Which one is correct, if any? To understand this, we have to see that there was an assumption here that made it impossible to tell apart who is the guy who is going to give us the well notion or well concept of causality at a given sense, which is this guy here. So you have to consider interactions. So let us consider a given potential, which I'm going to write in this way. You might interpret Q as being an unstable oscillator. Let's put it this way. So it doesn't have, let's say, it's not a damped oscillator. And let's pretend that its frequencies, its natural frequency, it's much smaller than omega 1. But let's keep it greater than omega 2 for reasons that will be clear once we generalize this to field theory. So this is just a small frequency, right? So in terms of the new variables, you can just write it in this way. So let's Q2 minus Q1, Q square. So lambda is a coupling constant. So suppose that you are doing perturbation theory, right? So that means that you will conceive corrections to your propagator. So your propagator is actually going to be written, instead of working with something like that, let's just call it in this way. This propagator will be corrected due to interactions with this new oscillator, with something that you can call as a self-energy correction, right? Since for the oscillator 1, the frequency associated with this stable oscillator is much less than it is, that means that the self-energy correction for the oscillator 1 will have an imaginary part. This imaginary part, as you can show, happens for frequencies greater than 4 omega squared. It's 4 because I put a Q square here. So it's like, you can imagine this guy here as an unstable particle decaying into all these stable oscillators. If it was a cube here, then it would be a 9 here. Then, if you analyze this close to the pole, so let's take the 1, right? So that's a minus here, that's a minus here, that's a minus here, that's a minus here. So let's kill it at epsilon here. So if you analyze this thing close to the pole, then this propagator would acquire this form here. So omega 1. Omega square minus omega 1 square minus I gamma. This guy here is the imaginary part of the self-energy contribution. So every time that the frequency is greater than this value, once you go close to the pole, the propagator associated with the oscillator 1 will behave just like this. So what is this thing telling us? This is telling us that once you consider interactions, the oscillator 1 develops a damping term. So it is in the sense that we can interpret this guy as describing an unstable particle. So if there isn't any external force forcing him to continue to oscillate, this damping term will make him oscillate and finish it as oscillations, right? Just like we are studying classical mechanics, the usual damped harmonic oscillator. So that means that for low frequencies or large times, the only oscillator that survives, or the only oscillators that survives, are the ones associated with the capital Q and Q2. And these are stable ones. So for low frequencies or large times, the only stuff that survives are the ones associated with, let's say, omega 2 oscillator and capital omega oscillators. So these guys are normal in the sense that the path integral then, I didn't write the path integral of the omega, the capital omega, but you can imagine that this is just an unstable oscillator, so it will give you a path integral in the same way as this guy here. So these guys here are giving our notion, our usual notion of causality. So causality, in this case, is an emergent phenomenon, in the sense that it only makes sense to talk about causality as we do in the limit of low frequencies. Because as soon as you have frequencies of order of the width of this guy, or times, short times, in comparison to of the inverse of the width of this guy, then you can have this extra notion of causality as well, so you cannot define a preferred notion of causality. You cannot define a preferred era of causality in which causal processes would make sense. So causality is a given emergent phenomenon, which appears already at the level of a pure simple example such as the Pi-Zullenbeck oscillator. So now we're going to see how does those things appear in a given field theory model. As I told you, one of the good motivations to consider these higher derivative theories is gravity. And the same phenomenon that we are seeing here happens as well in quadratic gravity. We are not going to see in full detail quadratic gravity because I will need more time to discuss this. But the main features of those guys here can be seen in a simple scalar field model, which we now going to study. So let's consider what I'm going to call the Lee-Wick scalar field model. So it's just a toy model, but it contains enough physics to understand what's happening here. And you'll be enough for our purposes and to give us a little bit of intuition what's happening. So let's study the Lee-Wick. Let's call Lee-Wick quantum field theories. Right? So our model. At the end of the class, if time permits, I'm going to touch a little bit about renormalization within Lee-Wick quantum field theories, and then I will change a little bit our model. But for now, I'm just going to consider this simple model. So let's say that we have the Lagrangian, which I'm going to write as L phi plus L chi plus a given interaction, which I can just write in phi chi dagger chi. Chi is a charged scalar field, so it's a complex scalar field, right? So L chi is just as normal as it can be. Demi chi dagger plus a mass term plus m square k dagger chi, perhaps a self-interacting term as well, k dagger square. Let's call it m chi, and L phi. It's something like f phi. Pretty normal, right? But suppose you can consider a mass here, just to be completely general, and then a higher derivative term, box phi square. So I'm considering the case in which m phi is much less than m chi. So you can envisage this in the limit of m phi going to 0 as a scalar proxy for a higher derivative QED. Because in this limit that m goes to 0, this field, this massless scalar field, will produce Coulomb-type interactions for this charged guy here. Well, I didn't want to consider this case here. It would be analogous to consider. In here, I'm going to consider, for instance, m is much greater than any of those masses. So that would be the case if I consider one of the masses to be greater than m, right? So that would make the other one as unstable. So it's like you have two regions of energy, right? A region where you're going to have a guy that is unstable, and then you're going to have the ghost guy as unstable as well. So I want to avoid this. I want to consider the mass associated with this guy, or the frequency of the oscillator 1, greater than any other frequency scale in the problem. So it's the same as here. I'm going to consider this guy here as energy scale, setting an energy scale much greater than any other energy scale that you can consider in the problem, right? So that's the idea. Right? Okay. No problem, right? That's my model. Let's try to study it. So it's a field theory generalization, what we were doing about the Pais-Uhlenbeck oscillator, right? Eventually, I'm going to take m phi as 0, but in principle, we can just let those guys in here. Just considering that we have this hierarchy of scales. Okay, so let's be pragmatic. I'm not going to discuss canonical quantization. I'm just going to discuss path integral quantization. Or, in the words of Feynman, shut up and calculate, right? Does it mean that we are solving our problems? Not quite. In the way that we are constructing the things, or at least it should be clear by now, also we have considered the path integral quantization of the Pi-Zullenbeck oscillator. We are considering guys, ghosts, who carry positive energy, but backwards in time. So that means that I'm going to interpret those guys as negative norm states. Of course, if you want to proceed, go further within canonical quantization, then you have to make sense out of it. So we can proceed along the lines that we have discussed yesterday concerning the indefinite metric in Hilbert spaces. But path integral is more pragmatic. It gives you a way to do the calculations. It gives you a way to give results, as Manuel was saying today in the morning. So it gives a way to produce results that in principle could be compared with experimental data, if any, if experimental data were available for this model, right? So it's exactly the sense that Feynman, or it's being said that Feynman also prophesied this sentence, right? So shut up and calculate and see what happens. So that's pretty much what we're going to do here, right? Okay, so let's do something similar that we have done to the Pi-Zullenbeck oscillator. In that part, we have split the description in a two oscillator description. So let's do the same thing here. So the ingredient, the basic ingredient is to add an auxiliary field, which I'm going to call eta. This field you add so that you can get rid of this guy here. But in such a way that if you integrate it out, you return to the usual Lagrangian. So, and this Lagrangian won't change. So I'm just going to consider this guy here for now, right? So that means that when you add this guy at the path integral and then you do what you have to do, you find something like this. Eta box phi plus m square, eta square, minus m square, phi square. For now, I'm going to eliminate this term because of this, right? But you can proceed with this, but just let's keep it simple, right? Now you define a field which I call A. So I do this splitting. And then I go to the path integral again. Then after these definitions, I find in the same way that I did for the Pi-Zullenbeck oscillator, two terms. So now let's just write it in this way. L tilde, right? So this is going to have a term just like that. Let's put the total Lagrangian because I want to add also the interaction term. So the total Lagrangian associated with the phi field, right? So I'm not going to write this part here because this part is kept untouched. So the total Lagrangian for the higher derivative field is transformed into, after these definitions, so we have a normal field, which I call A, a normal scalar field. Doesn't have a mass, but it has that interaction term, so minus G, A, K dagger K. And another field with a minus in it from its part in the Lagrangian. Eta, eta minus m square, eta square, minus G, eta, K dagger Q. So now, if I consider just the path integral of this higher derivative field, I see that I obtain a result which factorizes, right? In terms of the A field, in terms of the eta field. Much in the same way that we did for the Pi-Zullenbeck oscillator. So, the path integral for the higher derivative field becomes, so of course, it depends on the chi field. So you cannot forget it. So now, before you have something like this, right? Let's call it the action with phi and chi. Now, the thing factorizes into one contribution, which I'm going to write it as S eta. S eta is just this guy here without the minus sign. So this is S eta. Another contribution, which is just SA, which is a normal contribution, right? In the sense that the path integral doesn't have a minus sign, usual minus signs are here. So eta ena I S A. Both of them depends on the eta, the chi, and here on A and chi. So you can proceed in the same way that we did before. In here, you add a term such as this, eta square minus. And here you add a term such as this, minus eta d4x a square, to make both path integrals convergent. If we focus on this part of the path integral, what can we obtain? Well, it's just a usual Gaussian path integral. So you just complete the square, as you will do in normal path integrals. The only difference is the minus here, so it's just as we discussed for the Pi-Zullenbeck oscillator. It's just a time-reversed path integral associated with this funny field, eta. So the path integral for the eta field reads, so this guy here, right? Adding this term as well, don't forget about it, is given by just an expression in this way, minus, so you have the S square, so you have G, right? I put a G. Yes, a G. Key dagger key X. Then you have a propagator, X minus X prime. And you have another term here, key dagger key X prime. And this propagator has the same form as before, but now with the spatial part, of course, which in momentum space looks like, so it's an I minus I, sorry. So it's 4, so Ky, K square, big M, M square, minus I epsilon, and a minus K dot X minus I. So, as we have seen for the Pie-Zullenbeck oscillator, the interpretation that we like to give to this guy is a guy that carries an arrow of causality different from the normal guys. So it's a time-reversed propagator. A propagator that is carrying positive energy, but in the backward time, in the backward sense of time that we are used to. In the same way, because of this minus signs in here. This minus sign here makes this guy a ghost. So that is a propagator for a ghost. Well, if you think of Ostrogradsky, as we discussed it yesterday, you would say that this theory is unstable even at low energies. But is that so? Is this what this result is telling us? Let's see. If we go to low energies, what happens? If we go to low energies, then this propagator becomes a delta function, right? In the usual way we do is just to ignore the dependence of the k square in the denominator, so you just have m squared. So this is just the usual Fourier transform associated with the Dirac delta function. So at low energies, all this guy here, which I'm going to call A, behave just like this. N minus I, D4 square, G square, right? Key dagger Q square. So as you remember, the Lagrangian associated with the chi field had a self-interaction term. So at low energies, this guy here just shifts the coupling constant with a minus sign, of course. Am I missing any factors? Let me see. Let me check, because I'm doing this calculation quite fast. Let me check if I'm missing any factors. No, it's cool. It's cool. Of course, I forgot the m square, right? I forgot the m square. So it's just an m square. So is it bad for lambda? No. Because even if it's a negative contribution to lambda, since we have weak coupling, otherwise we wouldn't be talking about perturbation theory, and since we are at low energies, that means that we are in energies far enough our mass scale here, this term is a tiny contribution to lambda. So low energies, this theory is just normal. So at low energies, the effective field theory that we would have obtained, it's normal. It's quite normal. Theory is normal. So that means that if we take the classical limit of this guy, The classical limit is also well behaved. You can ask, of course, what I mean by classical limit. So I must consider wavelengths which are much greater than the Compton wavelength of the chi field. So you can envisage the classical limit in this way. So everything is normal, right? So again, did we solve the Ostrogradski problem? No. We are just finding a way that we can circumvent the problem and generate results that make sense, that we wish to believe. That is what we are doing. That is exactly what the path integral is telling us. We start with a higher derivative Lagrangian. We did some techniques to integrate. We find, again, the dwelling arrows of causality. I didn't do the path integral associated with this guy, but it's the same as the oscillator case. And then I went to low energies. If I stuck to the Ostrogradski interpretation, I should have found instabilities at low energies, but I don't find. That's what the path integral is telling us. So, of course, this is just a convenient description of how to derive those guys, but I don't need to use a two-field description. I can use directly a description keeping the higher derivative term until the end. That would develop into something that we would see as a quartic propagator in momentum space. So these theories, right? These theories develop quartic propagators. So I'm going to write in momentum space, of course, propagators. Q square, phi mu square. So it's, no, we don't need two i's anymore. Q square minus Q square, Q to the 4, M square. Of course, if we are considering interactions, as we are doing, we have to consider a given correction, given quantum correction to this propagator. So it comes as a self-energy term after you do a suitable resummation in the geometric series associated with the quantum corrections of the propagator. So as we have seen, this guy here develops an imaginary part. Since M is much greater than M phi and M phi, and we are just considering M phi close to 0. So near the pole, let's say, near the massive ghost pole, you can just do a Taylor series expansion, and you're going to find a result resembling what we have written here, right? And this gamma here is the imaginary part of this guy here calculated at M square. That's what the usual calculation will give it to you. This is just plain usual quantum field theory stuff. Nothing new about it, but we have two different signs in here. Right? These two different signs are good for something that we're going to discuss in a bit called unitarity. So now you may feel tempted to argue that this propagator, which is describing a massless field and a massive ghost field, can be written using, for instance, something that we call narrow width approximation, and the fact that you can use partial fraction decomposition in the for the whole stuff in here. So you might feel tempted to write the propagator in this way. So you might feel tempted to write the propagator in this way. You may feel tempted to argue for a given representation of the propagator. So you will write something like this. I, so you have I, Q square, minus I, Q square, minus M square, minus I gamma. In terms of the physics describing this spectrum, you won't be wrong, because this form of the propagator is yelling at us that this is propagating a massless normal field, which carry the usual xi epsilons, and a funny guy, a massive ghost field. But this form cannot be right. It violates a lot of stuff. For instance, it gives an imaginary part for space like Q square, which is bad, right? An imaginary part means things that are propagating, so things that are on shell, right? So in my conventions, on shell means Q square equals M square. In this case, Q square capital M square. So this cannot be space-like, right? But in this situation, you can have this. So it violates basic principles in quantum field theory. So this is not a good representation of this propagator. But that was precisely what the calculations seemed to tell us, right? So there must be a way to circumvent this, or at least give a representation where things can be better defined. And it is, you can give this. This was given a long time ago by Coleman in one of his famous lectures about Lee-Wick field theory. So now we have moved on the topic. Let's discuss now the form of the propagator which you should take once you are considering imaginary parts, or if you want to discuss unitarity, for instance. So, yes. What's the name of what? It doesn't have a particular name. Given. A given representation. Sorry. That is why I wrote the lecture notes and I upload them to the website, right? So you wouldn't have to bother to understand my handwriting. This is enough once you are close to the massive ghost pole. Of course, this part is enough. But if you want to have a description which is manifest these two particles, one of them, propagating in your theory, then you would be tempted to write something like that, using partial fractions, right? Because suppose you didn't have this quantum correction. Then you can just do partial fractions, and you will find this term without the width, right? And then you can argue, okay, so since this guy has quantum corrections, and this guy, this mass, is much bigger than all other masses, the quantum corrections will give an imaginary part. To whom? To this guy. So let's just put in a width and be happy with what we have in hands. So again, as far as the spectrum is concerned, you are not totally incorrect, because this is what it's telling us, right? A massless particle and a massive particle. But that guy here, in this way, can only be an approximation. An approximation of what? This is what we're going to discuss now. So let us call it modify Källén-Lehmann representation. So a long time ago, these guys here, this gentleman, produced a non-perturbative representation for the propagator, just using analytic properties of the propagator. So, in a sense, just poles and cuts and branch cuts. So now, let us assume, actually, I'm going to say let us assume, but it's something that you calculate. So it's not an assumption, it's something that you can calculate. But anyway, let us assume the presence of a branch cut singularity. Branch cut singularity. Above Q square equals 4m chi square. This is the multiparticle threshold. So that means that energy is greater than this guy. The propagator associated with the particle acquires an imaginary part in the mass, just like we did. So now our propagator has, in principle, 3 features, right? We have these 2 poles, and we have this branch cut singularity. So let's go to the complex QS square plane. The branch cut, yes. And that is why you have the imaginary part. That is why you have imaginary parts. Loop corrections give you this, right? So we are in the complex Q-square plane. So we have the branch cut starting at 4m chi square. So this is the branch cut, right? You have the massless pole. I'm running out of colors. So we have a massless pole here. And you have this pole here, which because of this change of sign is slightly above the real axis, right? So it's here. It has to be here, right? Because it's after the branch cut. If it was here, it wasn't supposed to be here. You'll be here just right. So it's at some point here, right? But now this description is because we are studying the branch of this many-value function given by the I-epsilon prescription, which means that we are approaching the branch cut just like this. But since we have a guy that carries an opposite error of causality, we would be able also to see what happens on the other side of the cut, which means taking a branch which goes like this. And then if we did, we would have found another pole. This pole is expected on the grounds of something that we call the Schwarz principle, that states that propagators should have this behavior. So the appearance of the other complex conjugate pole is actually mandatory. So now we don't just have 3 features, we have 4 features. We have 2 complex conjugate poles, we have the branch cut, and we have the massless normal pole. But we have an additional feature, right? Since this propagator falls as 1 over q to the 4th, it decays fast to infinity, right? So we can use the Cauchy formula. What the Cauchy formula states for us. Let's take a function, fq squared, which is analytic in a given region of the complex plane, inside a given contour, so you can just write the function in this way, right? Minus q. C minus q squared, sorry. Right? That's what the Cauchy formula tells us. For a given contour. So what should be the contour here? It should be a contour that doesn't have these contributions, but at the same time is counting on them. So you have to, I'm going to put those guys slightly above what I was going to write, but you know, it's just something to make it clear. So it has to be a contour in which you write, so it's contour, you see it here, so you put it in here. So it's, I'm terrible in drawings. Yes, that's it. That's it. That's my drawing. That's it. So it's something that, it doesn't deviate, right? So it gives a contribution, but outside the contour. So it's something like this. It's a small sphere here, and then you get here, and then you have a small sphere here, and then you close in infinity. Since this guy is well behaved at infinity, it goes to 0, so you can take this contour to infinity without any problems, right? So when you do that, you get the contribution from this pole. It's not inside the contour, but it's within this little contour. So once you do the residue calculation, this guy here approaching 0, but it develops a contribution from this pole. And the same for this guy, and the same for this guy. And of course, the contribution coming from the branch cut. Right? So the idea is to take this guy as small as possible, but never to 0, right? But at the end of the calculations, you just have an integral along the real axis from here to infinity. And you have a function that encodes this contribution coming from the branch cut. This is just an usual calculation, right? In any course of mathematical physics, probably you have seen those things. So it's not a big deal, actually, right? So let's do the calculation. After you do the calculation, what you find is the following. So now your propagator can be written as normal pole, right? Now let's call it this pole with a residue. I'm going to just write like this. When mu square is associated with this pole, this pole, the complex conjugated part, right, plus the part that encodes the information on the branch cut. So it starts at chi square, 4m square, infinity, ds. And this is what we call the spectral function, which is positive, always positive. Q square minus s plus I epsilon. So rho s is always positive. So this is associated with imaginary parts of this guy. Always that you cross a cut, you find a discontinuity, and this discontinuity is given by the imaginary part. Just complex analysis, guys. Nothing really special. But now this form is good for us. This form doesn't develop an imaginary part for space like Q, only for time like, as you can probably check. It's a good exercise as well. Better than this, the only part that gives you an imaginary thing to your propagator is this guy. It's obvious, right? Of course, you have the imaginary part coming from this guy as well. But as far as the ghost is concerned, the only contribution that gives you an imaginary part is this guy, right? But as soon as m is greater than 4m squared, because that is when the delta function, you know this, right? Principal value of x minus plus p delta x. You know this formula, right? So once you use this formula in here, for this delta function to be satisfied, the mass of the ghost should be within this interval. So it should be greater than this. So it is exactly where you give the imaginary part. Oh, there is a y here. Sorry, there is a y here. So it is the point where you give an imaginary part. And these guys are complex conjugate of each other, so they cannot produce an imaginary part. And the good thing about it is that this contribution is as normal as possible, right? It doesn't have a minus sign in front of it. It has the plus I epsilon. But this contribution should be expected, because if we look at our first form of the propagator, the fact that we have two funny signs means that this guy here is going to produce an imaginary part which has the same sign as an usual unstable particle, a normal unstable particle. So to have a contribution giving the imaginary part as normal as possible is expected because you have these two change of signs. If we had just one, then we'll be running into problems. Then these things, in principle, couldn't have a better definition, as we're trying to do. But there's another feature here that justifies we consider just that term. Ah, but you said that this term, that representation is not correct. Is an approximation. So how we see this? Then you have to do some numerics, and the numerics proves to you that this guy here, the contribution of this guy here, cancels the resonant behavior of this guy here. So if you're considering the sum of those guys here, so minus beta squared, you can only see this using two things, numerics, a simple numerical calculation, or using the narrow width approximation. I'm going to discuss the narrow width approximation in a minute. So if you just consider these guys here, this contribution gives you a non-resonant piece. So by non-resonant piece, I mean it doesn't give you a pole-like contribution. So in practice, there are only two poles, this guy and this guy. That representation. So it's not as bad as we thought, right? And this guy, this cancellation, is exact using the narrow width approximation. The narrow width approximation is an approximation that you can always use when you are at weak coupling. Because when you are at weak coupling, the coupling with the decay products of the unstable particle are really small. So in the sense, only the resonant production matters, right? So in this case, you have a form for the spectral function. So it goes just like this, something like this. So I'm going to write, then I'm going to explain. So gamma is the width, and I'm calling now mu square as m square plus I gamma m. So once you are in the narrow width approximation, you have a general form for the spectrum function, a bright Wigner shape. Because to be in a narrow width approximation means this unstable particle may be confused with a stable particle. So the spectrum function has to be picked at some point, associated with what we would call the mass of this particle, right? So if you take this guy, plug it in, since this is highly picked around m squared, and go to all the real line and use just usual contour methods, what you're going to find, assuming that beta and beta square is close to 1, which is always the case if you are working with renormalized fields and on-shell renormalization, then this guy is going to produce exactly the same contribution with this guy, but with an opposite sign. So they cancel exactly. This is a very good calculation. If you never did this, it's a good calculation. So this gives you a way to understand our approximation, right? Okay, so now let's talk about two things which unfortunately I won't have time to develop further, but I can give you at least some parts of details in here, which are stability and unitarity. Remember that we have started all this subject discussing about osteographic instabilities, right? So now the question would be, is the quantum theory stable or not? Well, we don't have a precise answer for that. What we can say is two things. One, as we've been dealing with these path integrals, as we have discussed yesterday concerning the canonical quantization of the Pi-Zullenbeck oscillator, the choice of the canonical coordinates that Ostrogradsky did, it's not the choice that quantum physics, especially the path integrals, do. In that case, he was concerned about recovering the Hamilton's equations. Of course, he was just in classical mechanics, so Euler-Lagrange equation, Hamilton's equations, they should give you the same outcomes, always. So that was the thing that he had in mind. But not exactly quantum physics. Quantum physics is really concerned about particles having positive kinetic energies. That's what makes sense. That's what makes you take, for instance, a creation operator acting on a given vacuum or vacuum state and creating a given particle with positive energy. That's what makes sense to us in quantum physics. So it's not clear that the Ostrogradsky choice makes sense in quantum physics. Or to put it in another way, it's not clear that our usual formulations, alternative formulations, such as Lagrangian and Hamiltonian, or Euclidean, Lorentzian, should all agree when we study higher derivative theories. I'm not claiming that they are different. I'm just saying that we just cannot jump to the conclusion straightforward that they always going to give you the same results. You have to do the calculation to show this.
But isn't that true for like interacting normal theories?
Yes, and the proof, you have to prove this. And the proof...
My question, isn't that true that you have to prove like case by case, like Euclidean and Lorentzian?
Yes, of course, but what...
Yes.
Yes, but you know the tools, right?
Know how to check it.
Yes. For the higher derivative theories, things are more subtle. So just do not take it for granted. Usually we take for granted because, okay, we always have the Dyson-Schwinger equation there, and can I take it and I can prove it? And then we took for granted, right? But for higher derivative theories, things are more subtle. So just be careful. That is why I'm just considering pathing integrals. Okay, so let's talk about a little bit of stability, right? I'm not saying, again, that I'm giving you the proof that those theories are stable. I'm just giving you a piece of evidence that they may be stable, right? So, the fact that our propagator, right, let's just do the approximation that we did. So, we just have this form of the propagator. S squared minus I. So suppose we are in the narrow width approximation. We did our approximations here, and we find this guy here. So the fact that you have a funny sign here means that it might be possible that your propagator, once you Fourier transform back to the coordinate space, will generate an exponential growing up. But that is not true. Suppose again that you are in the narrow width approximation. So this approximate form is established once we have the modified Lehmann representation, right? So this guy here is approximately constant, small but constant. So that means that we can just perform our usual Fourier transform in this guy here. And not use any different contour. Let's just use the usual contour, usual Feynman contour. So use the standard Feynman contour. Why is that important? Because as you're going to see in the old literature, take for instance a paper by Bauer and Gross, which depicts clearly this is what I'm going to talk about. And also the original papers by Lee and Wick, in order to expurge the theory of exponentially growing modes, you cannot use the standard Feynman contour. But that's not entirely correct. Not in this situation, because if you take this guy here and do the Fourier transform, where are the poles of this thing, right? You have 4 poles, right? You have the poles associated with this guy here, which are here and here. So these are the poles associated with this guy here. But you also have the poles associated with this guy here. Which are here and here. And these are, let's put it in blue, right? Q0 square equals, let's call it Q square plus M square. Let's call it EQ. So this is UQ plus I gamma. So this is just Q plus minus this guy here. So this is a small guy, so let's just do a a Taylor expansion, so this is just an UQ plus E gamma over 2 UQ. Am I correct? UQ, you put in evidence. Let's put a UQ square, right? Yeah, that's square root of UQ square. So UQ square, EQ, so 1 gamma over UQ square. You Taylor expand the square root, that's a 2, so you get UQ square in the denominator, UQ in the numerator, so just UQ. So that gives you an imaginary part, right? So these are the tuples. For small gamma, right? For small gamma. So let's take, for instance, the propagator written in the usual sense as a forward and a backward propagation. So in the way that you are going to define something like that. So you have a forward, theta t minus theta, and a backward, I, right? Theta. So for this guy, you close the contour downstairs, right? And you pick up these two poles. So once you do the calculation, this guy is going to produce something like this. I'm not caring about the I factors in here, but anyway, you're going to produce something like this. These two poles in here are just, you know, Q and Q. So you're just going to produce something like this, right? But then you also have a guy which behaves like this, t minus t prime, right? T minus t prime. But this pole here, right? It has a minus here. So a minus here combined with this minus here produces a decaying exponential, right? Gamma 2 EQ t minus t prime. Right? Are you following me? That's a minus here, and that's a minus here. So it's I squared. I squared, it's a minus. So it's a decaying exponential. And you can do the same as for this guy here. So you have those signs reversed, but not the exponential. Because now, for the backwards guy, you would close the contour upstairs. And then you get this guy here. But then you have a plus sign here, right? For the, let me write it in this way, so it's going to be more correct. So this is the guy that I'm talking about. So what happens is the following. You have a guy that carries positive energy forward, which is the normal guy, and we also have a funny guy that carries positive energy, because this is positive, but backwards in time, but decays. So the appearance of this guy here, this exponential decay, means that this propagator is not propagating exponentially growing modes, even using standard Feynman contours. That is precisely what our calculation is telling us. So it seems that everything here, right, behaves as normal as possible. Can you give me 10 more minutes, guys? 10 more minutes equals 20, right? Okay. Okay, there's a bunch of things that I could have discussed, but it's in the lecture notes, so I'll just leave you guys to see any more details. So let's move on and try to discuss at least a little bit unitarity.
But wouldn't the backward one have an opposite behavior?
Opposite, by that you mean?
The exponential growing.
That's the backwards. Oh, the backwards, no, it changed the sign. Right? The backwards, you close the counter upstairs, in the upper side. But then you have a plus sign here, and you're taking this mode, this zero, right? This pole. So you have plus I, so it's a minus again. You have two I's, of course. You have two I's. You have two I's. No pun, no pun, no pun. And of course, there are also the denominators, right? I didn't wrote it, but you know, you can write it the denominators, right? E gamma over 3k. Anyway, so let's talk about a little bit of unitarity, right? So what is unitarity? Unitarity is a fancy way to say that probabilities should sum up to 1, right? So in the usual interpretation of quantum mechanics, what we can talk about is probability. So unitarity, it's one of the dearest concepts in quantum theory. So unitarity means a statement about scattering amplitudes. So usually you define a scattering matrix. Usually you separate the scattering matrix into a forward scattering part plus something that we call the transfer matrix. And then we define the scattering amplitudes usually associated with this T. So unitarity means that these equations should be satisfied. So suppose you are looking at a reaction, say you have a given initial particles going to a given final state of particles. So this guy here should be satisfied. Star I. So this is just sum over J, F, T square, J, J, T, I. So this sum here is a sum over everything that could go on shell here. So that means 2 particle states, 3 particle states, multi-particle states. So using the usual definition of this guy, which is something like that, you have a delta function associated with the conservation of energy momentum and a given scattering matrix element. Usually we call this guy as a scattering amplitude, right? So this guy that you usually call the optical theorem in analogy with the classical result that the total cross-section is proportional to the forward scattering, right? So we will obtain this guy here. So optical theorem, or generalized optical theorem. So you have, let's call it I to the F. There's an I here. Yeah, there's an I here. Usually there is an I here. It's just a phase, but anyway. Minus m square F to I. Then you have a bunch of sums over all possible final states, so you have m square. Let's not call it F, let's call it I. Let's call it I. So it's I to F. That's I to I. No, it's correct. I to F, I to big I, times a delta function here. And times another delta function associated with the one for overall energy momentum conservation. So this is the optical theorem. So we like to prove this theorem. Of course, this integral is just the Lorentz invariant phase space. So it's always something like that. It's d to the 4k, 2p4, theta positive, theta q square, if it has a mass m square, or you can do this integral, it's d square, 2 q square plus m square root, square root. So this is the famous Lorentz invariant phase space, right? So what's the usual idea? The usual idea is to find which is your spectrum, right? Because your spectrum, your collection, your set of excitations of particles will enter here. So that means that every time that you want to calculate the imaginary part of a given amplitude, you will not vanish unless some of the particles within the Feynman diagrams will be on shell. And that means that the internal propagators describing these excitations will be on shell. The imaginary part of a given propagator, q square, m square, plus I epsilon, is a delta function, right? It's minus pi delta q square over m square. So every time that q square equals m square, this propagator acquires an imaginary part. But that is only possible when the particle associated with this propagator is on shell. And that is exactly what happens in here. So you need to know what is your spectrum. So usually what we do, we go to the free theory, quantize the theory, right? And identify the spectrum. You can use canonical quantization, path integral, doesn't matter. And then you turn on indirections to see what happens. Start to calculate loops. And then you see that some of the particles, as our ghost particle that we've been discussing until now, acquires the self-energy correction associated with their propagators, acquires an imaginary part. So if it acquires an imaginary part, that means that this propagator is describing an unstable particle. So if it is unstable, it's not part of the asymptotic spectrum anymore. So this raises an issue, right? If we start from the free theory, you would say that this particle should be included in the what we call the unitary sum. But once you turn in directions, this particle is not in the asymptotic spectrum anymore. So the question is, should we include those particles in unitary sums or not? So Veltman answered this question back in the 60s in a famous paper in the 63. He basically says, no, we don't. He developed something that we call the largest time equation to prove this. So he basically says no. So he says, Veltman. Do not include unstable particles or unstable propagators associated with unstable particles in unitary sums. Unitary T-sums. Unitary T-sums. So once you don't do this and follow Veltman's procedure, you can prove that the theory respects the optical theorem. The theory is unitary once you include only the stable particles on your spectrum. But then, now you remember, our ghost particle is unstable, right? So it should not be included in the spectrum, right? Yes. And you prove this. How you prove this? First of all, you might consider the lemma representation that we just considered. And then you have to consider something that we call cut propagators. That in the end, what appears in that part are delta functions. And this guy here is what we call cut propagators, or Whiteman functions. Positive frequency Whiteman functions in momentum space. So you have to take the modified lemma representation that you just gave and develop the cut propagators associated with that lemma representation. It's possible. I gave the form, the closed form for you guys in the lecture notes. So that is the idea, to prove. And then there is this new set of Feynman rules development introduced just to prove this formula. But the basic idea is the following. These cut propagators in momentum space can be written in this form. So I'm going to give you the form with the spectral representation. So the cut propagators have this form. G plus minus, you can have the negative. Minus 1 over pi. In momentum space. No, let's go to the momentum space. So we have this form. Plus minus p squared. For a normal particle, right? The only difference for the ghost particle is a bunch of minus signs that appear differently. But it has the same form. So you have a delta function here, p squared minus s, and you have the spectrum representation, right? But the LSC reduction formula tells us that the S matrix just projects out one particle states. How is that? If we remember the formula for a given S matrix element for a scalar field, say, it has this form, right? So the LSC reduction formula, it's something like this. F of I. So we have a bunch of integrals here. So it's I. So it's d for x to p 4. So it's n minus I by I xi box. Let's say it's minus box plus tonight particle square times everything that comes here or here. I'm just changing a sign here just to present a particle that's coming in the initial state, or a particle that is in the final state. So it's f times xf times the box plus mi squared. Actually, I should have been more careful because this guy appears in here, but anyway. Times time order product of a bunch of fields, right? That's square f. So what is this telling us? If you go to momentum space, this guy is going to have a bunch of contributions, such as propagators and some amputated parts. Every time that you have this guy here, can combine to this guy here and kills, right? If you don't have contributions that have the propagator in here, they have this form in the denominator, this guy will just kill this guy, right? So this is what I mean by projecting out one particle states, which are the states that appear as poles in our complex plane. And how does that connect with our discussion? It connects with this guy. for stable particles, using O'Shaw normalization, you can prove, this is just a textbook proof, that the spectral function is always given by a delta function times another combination that encodes the imaginary part coming from interactions. This is the guy that is associated with the one particle state. Unstable particles do not have this contribution, because unstable particles do not have one particle states. Remember, unstable particles are always after the branch cut. So they doesn't appear as poles on the real line. They appear as poles in the complex plane. They're shifted from the real line because of the interactions, right? So you cannot have this contribution here. So that means that after you consider these propagators, these cut propagators, you use the same procedure as Veltman did in the 60s. You arrive at an equation which looks like that one, but for unstable particles, you will never, ever produce the Lorentz invariant phase space. And the Lorentz invariant phase space is the one thing that is telling that you have a one particle state. You won't produce that for unstable particles. The whole proof, in details, are in the papers, but also is in the lecture notes that I just gave to you guys. So that means that these theories are actually unitary, because the ghost is actually an unstable particle. So that is why I reinforce the necessity of considering interactions, because the interactions give you the information about the presence of this width, but also gives you the information that the theory can be unitary. Of course, we were discussing about the situation in which these ghosts can be described using the narrow width approximation, right? We use that. But then there is a problem. There is a fancy way to prove this guy in textbooks, going through something that we call the cutting rules. The cutting rules mean that you're going to roughly replace all internal propagators that appear here with cut propagators. And you receive this name cut because in terms of drawings, you are cutting lines within your diagram. So, for instance, the usual sense is just to describe that part as a cutting equation. So you just describe it as 2 times the imaginary part of the amplitude equals this sum here, PF. So you have every particle that can enter in, all internal lines that appear here that you are cutting, and then the particles that gets here. So to cut an internal line means replace a usual propagator, but it's cut version. In fact, you can use this thing to construct amplitudes. This is something that we call the unitarity method. Usually, a 1 particle cut means a pole. A 2 particle cut means a branch cut, and so on and so forth. But then you can analyze the structure, the analytical structure of the amplitude, given various types of cuts, which means cuts many of the internal lines inside your diagram, and then you can try to reconstruct the amplitude, the whole amplitude, just using its analytic structure. This is something that we tried to do back in the 60s, something that we call the S-matrix program. But that program was doomed to fail because they address a very broad question, which was, given an analytic structure of a given function, can I recover in its entirety? So it's a very, very, very difficult problem to answer. You know, of course, they weren't able to answer this. But here, we don't need to know an arbitrary function. We have a set of functions that we want to know, which are the Feynman integrals. So that is an improvement. So you can use these methods to construct the amplitude. So suppose we do this for, let's say, a bubble integral. But let's say that the bubble integral has an unstable particle and a ghost. So in momentum space, this would look like this part of the amplitude, something like that. So I, so let's call it the external momentum as P, so let's P minus K, K, so P minus K square. Let's say that the stable particle is massless, and then you have this guy also K square minus M square. Of course, let's put the width. We are in the narrow width approximation, so we can consider this. So our unstable particle is as unstable as is possible, right? The problem is, if you do this and use the Feynman prescription, the Feynman contour, I mean, then your amplitude won't give an imaginary part. And the problem is, you can do the same calculation using the quartic propagator, everything, and splitting everything in terms of using fractal decompositions. You can do that. You are considering that the massive goes as stable as possible, right? And then if you do that, or if you just use the spectral contribution from the Lehmann representation, you will find an imaginary part. Of course, Unitarity tells you that you should find this imaginary part. Then the problem is to use the Feynman contour for this kind of integrals. Or to put it in another way, to cut a ghost unstable particle. When you do that in the narrow width approximation, you cannot use the Feynman contour. The Feynman contour is just this, right? You have a particle with a given pole, right? Right? So the Feynman contour is just like this. Now your poles are a bit funny, right? Of course, you have more than these two poles. I'm just concentrating on the normal poles, and now I'm going to write about the non-normal poles, the ghost poles. The ghost poles are here. So what you do to prove the cutting rules using the narrow width approximation is to use another deformation of the Feynman prescription. So you use what we call the Lee-Wick contour, which is just a trick when you cut these unstable particles. So you just follow something like this. So you see, this pole and this pole are the positive energy poles. So the idea is, if you have a positive energy pole that is under the contour, it stays under the contour. There is a further proof on this in the lecture notes, which I won't have time to address here, but in the lecture notes, it's written with further details, how you do that and how you should choose the Lee-Wick contour in these cases. But you have to imagine the Lee-Wick contour as a trick, because you are cutting an unstable ghost line. Otherwise, you can just use the Lehmann representation and you'll be fine. Actually, tomorrow we're going to calculate an amplitude using the Lehmann representation and using the Lee-Wick contour. There are further additional things that we should do, but I'm not just going to discuss right now because time is forbidding me to do that. So what's rest for us to do? I want to talk a little bit about causality, a little bit more than I just did. And then I'm going to do the applications tomorrow. And then we're going to see a little bit of renormalization, which I didn't have much time to discuss now, but anyway. And that's it. Further details in the lecture notes, guys. Thanks.
I know that in standard quantum field theory, you usually only care about final initial states, asymptotic states. But when you're discussing unitarity, as you said, usual quantum mechanics, we have a continuity equation that should be valid from start to finish from your whatever quantum system. And nowadays, especially in quantum gravity, some situations not that you wish, but might be a signal of your quantum gravity theory if you have a breaking of unitarity in some point of your system. So this Veltman proof that your theory is unitary, is that saying that's unitary, like it's unitary in the final initial states, or it's unitary everywhere, and I shouldn't expect any intermediary breaking of unitarity?
In Minkowski space, you shouldn't expect for... No. In curved space is something else, because then in curved space, you don't know how to define a particle in a general sense. You don't have, in a general sense, time-like Killing vectors available for you. So the discussion of unitarity is more subtle in this way, right? So that means that first you have to define what you mean by unitarity. Here, since we are in Minkowski space-time, there is a very well notion of what is a vacuum. So you can define no interacting particles in the initial state and no interacting particles in the final state. That may not be available in a curved space-time. Say, for instance, de Sitter. De Sitter, it's hard to do that, even though there are recent proposals of a S matrix in de Sitter. But then you have to deviate a little bit of some related stuff that you would have in Minkowski space-time. So that is a given subtle discussion, right?
But if I have another definition of my vacuum in a curved space-time, I can, in principle, feel that
but it's not unique. But it's not unique. That's the point. Say, for instance, say you are quantizing a field in a Schwarzschild background. You have at least 3 vacua.
I'm thinking about cosmology,
You also have different coordinatizations, right? And these different coordinatizations will give you different notions of vacuum. So it's difficult. I'm not saying that in principle you can construct. You can try to do that, but you won't have the same status as it has in Minkowski space-time, right? Things are more subtle.
What I'm asking is, to construct the idea of unitarity in curved space-time, I would have to have a vacuum that I can define.
Yeah, because what lies behind this thing here is this. This is a formula. I'm not going to give you further details because I'll have to use another hour. But what lies is the ability to prove that this guy can be written as a creation operator, creation annihilation. I think it's an annihilation operator plus P minus P times something like here. This is the key results to prove the LSSE reduction formula. So you see, he appears those guys here. I think it's a creation operator, right? I think it's a creation operator. So that is the idea, that you have free fields, no interactions. But in a curved space-time, you have at least one, gravity. So even if in the initial state, you don't have the interaction with the gravity, let's suppose you don't, in the final interactions, you have. So you have to keep up the production of particles associated, for instance, with an expansion of the universe. So you have to keep up with that in order to describe everything else. It's possible, maybe, but it's difficult, right?
So why would we expect that quantum gravity theory? Shouldn't we expect the opposite?
Well, the idea is, if your theory is sensible using a flat space, then you can start to talk about the curved space. If your theory doesn't make sense even in Minkowski space, then it's hard to believe that it's going to make sense in the curved space in the general sense, no?
That's the mistake. I think that gravity is a theory that has to work in flat space. Gravity is flat space, is curved space, everything. So we are expecting gravity to be something that it shouldn't be expected.
Yeah, but that's something that Weinberg challenged in his book. That is something that you would say that gravity is always to be connected with the geometry of space-time. But it's not clear that it's correct. It's not clear. I mean, classically it is. Classically we learn that it's okay. But it can be just an analogy, right? Actually, if you look at the modern theory, the effective field theory, and everything that this amplitudes program is telling us, actually gravity may be viewed as a quantum field theory, or as a quantum theory. Let's say we are string theorists, for instance, of a spin-2 particle. So you don't need geometry. Geometry is completely unnecessary in the quantum. Yeah.
As the name says, it's linked.
I don't know. Is it? I'm not claiming that I'm correct. I'm just saying that it is a way to think of it. So,
How do you deal with unitarity in this context?
you just use this, for instance, right? Of course, depending on your approach, unitarity is more subtle than the others. Say, for instance, string theory. String theory is much more subtle. The idea is the same, right? You have some sort of optical theorem, you have a bunch of intermediate particles because you have a tower of massive higher spin particles, but things are more subtle. But you can describe unitarity. In that context, right, curved space-time means something else. Curved space-time means taking the string, propagating on a curved background, for instance. You know. And then now you don't have a linear sigma model, you have a non-linear sigma model. And then you have to impose Weyl invariance. And then you prove that you find Einstein's equations of motion plus a bunch of other things. Further questions? Do you feel uneasy? You should feel uneasy. This is not obvious. This is not straightforward. And that's the fun part, right? The fun part is these things are not obvious. That's the fun. You're still here. Sim.
De início, você introduziu que uma brincadeira que você queria conseguir fazer as integrais, para conseguir
Sim.
computar elas, né?
Sim, sim.
causalidade. Só que, beleza.
Sim, porque transforma um dos caras em um cara instável, né?
Beleza, mas
Então ele decai com o tempo, né? Então ele não aparece no espectro assintótico. Essa é a ideia.
tipo, esse caráter que você inseriu, ele é o jeito mais seguro de você, o epsilon, né?
Sim, é o
Ele é o
jeito
jeito
mais
mais seguro, assim, mais
seguro,
safe.
simples,
Só que se
exatamente.
você